So sulfur is immediately underneath oxygen on the periodic table. They're both in group 6A, and as you go down on the periodic table, elements become a little larger, and so sulfur is bigger than oxygen. But otherwise, because they're both in group 6A, they have the same number of valence electrons, and that means that they have very similar chemistries. So they both, for example, would have, if they're neutral, would have 2 bonds and 2 lone pairs. And so sulfur forms similar or analogous functional groups to the ones that oxygen forms. So if you think of an alcohol being oxygen, like you have a carbon chain bonded to OH, there is a sulfur analog to that, and that is called a thiol. And a thiol is a carbon chain, instead of bonded to oxygen and then hydrogen, it's bonded to sulfur and then hydrogen. And thiols can do a whole bunch of different things, but one of the key things that they do is they help to maintain the structure of proteins. They help to strengthen proteins because proteins, if you think of them as long chains, each little piece, each link in the chain that it's made up of is an amino acid. And there is one amino acid called cysteine that has a thiol coming off of the end of it. So it has this SH. And what ends up happening is that if you have 2 thiols, so in the case of a protein, you would have 2 cysteines, and they would both have this SH. When they come together, they can sort of snap together so that you would have a bond between the 2 sulfurs. And you have these 2 sulfurs bonded, that bond is called a disulfide bond. So when 2 sulfurs are bonded, it's a disulfide bond. And that is a covalent bond that helps to strengthen the connection between amino acids that could be on very different parts of a chain. And when they come together to bond in this way, they force the chain to be in a certain shape. And so they help to give structure to proteins, and they help to strengthen proteins. So for example, microbes that can survive in boiling water, like the microbes that live in the boiling hot springs in Yellowstone National Park, those survive in boiling water because they have lots of these disulfide bonds keeping their protons together, or keeping their atoms together, their proteins together, even when there's a lot of heat jostling them around. Our proteins don't have as many disulfide bonds, so when we jump into boiling water, our proteins just fall apart, and in other words, our tissues come apart. So that's one thing. And the other thing is it strengthens proteins, bonds like this, these disulfide bonds. So for example, the reason your fingernails are harder than your cheeks is because the proteins in them have more of these disulfide bonds. The reason why a horse's hoof is harder than your fingernails is because it has even more disulfide bonds. So the ability of these thiols to come together to form a disulfide bond ends up being biologically pretty significant. And so it's worthwhile, I think, to take some time to think about how that sort of reaction could happen. Now we're going to think about it from the perspective of like a synthetic organic chemist. But everything we're going to talk about has an analogy in biology. It has molecules that play the same roles as what we're about to see. They just look different. So on the test, what the question will be is, and this will be word for word the question, the only difference I'm going to make is I'll change the thiol I give you, but the question will say exactly what is in green here. Draw the mechanism for the oxidation of the following thiols to form a disulfide bond using sodium hydroxide and bromine. Now I'm going to give you, in this particular example that we're going to work through, 3 carbons with the thiol, and all I would change in the test is the number of carbons on the thiol. Okay, so we have NaOH and bromine. We want to show how you can use those to turn this thiol into something that has this very biologically significant disulfide bond. So, let's imagine, and now we draw these individual molecules, but of course, every time you exhale, you breathe out more atoms than there are stars in our galaxy. And so anytime we draw these are really shorthand for hundreds of trillions of this molecule. So there's going to be another one of these present for sure in our container. And if you want to know, ultimately we would like these two molecules to stick together. And when you're trying to figure out how things would stick together, look for nucleophiles and electrophiles, slightly negative places and slightly positive places. The sulfur has two lone pairs, just like oxygen would. And it's pretty electronegative, not quite as electronegative as oxygen, but it pulls electrons towards itself, so it's slightly negative. And that's true in both of these. Oops, that's true in both of these. For both of these sulfurs, two lone pairs, and the slight negative charge. And whatever it's bonded to is losing a little bit of that electron density. That's what makes the sulfur slightly negative, the fact that it's stealing electrons from these other places. Now, ideally, we know we want to form this disulfide bond, a bond between the two sulfurs, and so we would love if somehow this one sulfur could just attack the other. But we have a bunch of obstacles to that. First of all, they're both negative charges. We can actually overcome that. We'll talk about how we can overcome that. But let's just assume for a second that this slightly negative thing could attack that other slightly negative thing. To form a new bond, you'd have to kick something off of the sulfur. What are you going to kick off? This hydrogen? In that case, you would have a hydrogen with a lone pair and a full negative charge. That's really unstable because hydrogen is the smallest atom on the periodic table and you're stuffing a full negative charge inside of it. It's going to be really, really reactive. It would just snap right back onto the molecule. So you wouldn't be able to kick that off. What if you tried to kick the other carbon off? Same thing. You would end up with this carbon chain, lone pair on that carbon, full negative charge, and carbon is not that much bigger than hydrogen. It's still a small space, and carbon is not especially attractive to electrons. It's not really electronegative. So you're forcing this full negative charge to be on a relatively small atom that's not really attractive to electrons. That also would be really unstable and would just snap right back onto the molecule. So a short way of saying everything we just explained with a little bit of jargon is to say that this molecule here does not have any good leaving groups. And so the first thing we would need to do is to put a good leaving group on that. Now, from Organic Chemistry 1, you would want to remember that the really awesome leaving groups are the halogens, things in group 7A. Fluorine, chlorine, bromine, and iodine, except not really fluorine. And the reason why these are good leaving groups is because they're gigantic. Chlorine is about the size of a methyl group, bromine is even bigger, iodine is a monster. It's enormous. Fluorine, the reason why fluorine doesn't work is because it's actually small. It's the size of a hydrogen. And because these atoms are so big, they can, if they have a full negative charge on them, they can spread it out over a big area. And if you spread charge out over a big area, it helps to stabilize it because at any given point, you'll have less charge and so less repulsion between the electrons. So the halogens are awesome leaving groups, and we would love to put an awesome leaving group on this sulfur. So let's react it with a halogen, and what the instructions in the question said is to use bromine. So that's the halogen we're going to use here. BR. Now, bromine, bonded to bromine, each of these bromines has equal electronegativity, and so there isn't going to be a partial charge on either of the bromines. There's no reason for these electrons to prefer one bromine to the other. But as this bromine molecule gets closer to the negative, or to the thiol, and to the negatively charged sulfur, because bromine is so big, so let's say we have this sulfur with this negative, or sulfur with this slightly negative charge here, because the bromine is so big, when the electrons in the bromine feel the negative charge, those electrons fly to the opposite end of the molecule. There's plenty of room. It's a gigantic atom. So this is bromine, right? So they all fly that way, and one side of the bromine becomes slightly positive, and the other side becomes slightly negative. And that gives sulfur an opening. Once this side is slightly positive, the lone pairs on sulfur can try to attack it. Now, that reaction can happen, but it wouldn't be very efficient because sulfur here is not the strongest of nucleophiles. It only has a slightly negative charge. So we can make that reaction more efficient by making sulfur a better nucleophile by turning this partial negative charge into a full negative charge. And we can do that by ripping off this hydrogen with a base. And that's where the sodium hydroxide comes in. So the first thing we're going to do is to add sodium hydroxide. And sodium hydroxide is an ionic compound. That sodium has very low electronegativity, so it's going to give its electrons away, become positive. The electrons go on to the oxygen here, which has a negative charge. And the sodium goes on, floats around the solution, lives its best life. So this hydroxide, the OH-, is prowling around. It sees the positive charge on this very vulnerable hydrogen. Hydrogen is always vulnerable because it's on the very outside of a molecule. It only can form one bond, so it's always exposed on its other side. It's very easy to reach. It's like low-hanging fruit. So that hydroxide attacks that hydrogen. Hydrogen can only form one bond, so if you're trying to form this bond here, you have to break another one. And the one you're going to break is the one that's already weakened by the difference in electronegativity. The electrons go toward the more electronegative atom. Now, okay, so what we're going to have here is this, and now the sulfur has its 3 lone pairs. This bond turned into a lone pair, and beautifully a full negative charge. So the sulfur now is a really good nucleophile. Now keep in mind, when we did this, we didn't just do this to one molecule. We did this to hundreds of trillions of molecules. We did this to the whole population of that thiol in our beaker. And so this other thiol will also now be missing its hydrogen. That would have been stolen by another second hydroxide floating in the solution. And it would also have the lone pair with the full negative charge. So just to keep that in mind. So we'll set that aside though for right now. So the whole reason why we got this full negative charge on sulfur was that it could more efficiently attack this bromine. So bromine gets close, all of the electrons in that gigantic large bromine atom go to one side, that side becomes negative, the other side of the atom becomes slightly positive, and that's the time when the sulfur sees its opening, and bam, it attacks the bromine. The electrons in this bond go onto the other bromine in order to make room for this new bond, and so you get this molecule here. So the sulfur still has the 2 lone pairs. That third lone pair becomes a bond to our beautiful leaving group. And of course, back in the corner, you've got that other bromine with its negative charge. Who knows what that decided to do? Probably it went to go hang out with the sodium somewhere else in the beaker. We're just going to throw it away as sludge at the end of the reaction once we separate it from our precious, precious products. Okay, so our goal was to put a good leaving group on that sulfur so that another sulfur can come in and have a chance at attacking this. And the sulfur is still slightly negative. Now, not quite as much because you have another electronegative atom here, but it still is pulling some electron density from this carbon here, which is slightly positive. But this sulfur, this thiol here, thiolate, because it has the negative charge, can attack this sulfur, and at first that might not seem natural. Why would it attack this sulfur? How could it even attack this sulfur if this has a negative charge and this has a slightly negative charge? And it can attack that sulfur for the same reason that the sulfur above was able to attack the bromine. Because sulfur is pretty big. Sulfur is underneath oxygen on the periodic table, and as you go down, atoms get bigger. So sulfur is pretty big, and so kind of like bromine, as this full charge gets close to the sulfur, the electrons in the sulfur flee to the opposite side, and the side close to the negative charge is left with a slight positive charge, and that is the opening. The thiolate attacks the sulfur, and the leaving group leaves, and magic, when the dust clears, you have the beautiful, the wonderful, the protein strengthening disulfide bond. And of course you've got the other bromine floating around. That does its own thing, not our concern. It's going to be tossed away with the sludge that we separate from this beautiful thing. And so we formed our disulfide bond. And the process, of course, in your body does not use sodium hydroxide and bromine, but the concept is the same. When your enzymes are trying to make this reaction happen, they replace the H on this thiol with a better leaving group. They do that by first turning the thiol into a better nucleophile by ripping this off with a biological base. And once that happens, it lets it attack a better leaving group, puts the better leaving group on there, and then brings it into contact with another cysteine. So you don't have to be able to explain the whole biological application of this, but what you do want to be able to do is to draw this mechanism here. Notice that the R group, the carbon chain, didn't matter at all, and that's the only thing that'll change. So that's the only way that the exam question would be different from this.